So there we go. It should be live right now. I can't see the icon here. Okay, I suspect. 1 second. So let me check if. Yeah, it is recording. So we're live right now. All right. All right. So let me move this up. So when you see these dots here, it's because I'm trying to move stuff out of the way on the screen. We have a small screen here. The lesson today, folks, is very important and really one of the last key facts that you need for calculus 2. So especially if you move on to calculus 2, this is super important. Is called the integration by substitution, or the substitution rule 4.5, the substitution rule. And folks, this is going to be extremely important. So this is very important. I would say key for Cal 2. So those of you who plan on taking Cal 2, I know that there isn't that many, but those of you who are planning to, math majors or other majors who are planning to, please be aware that this is a really important topic. Now, there's two issues with this, two distinct things with this lesson. So number one, so we need to explain how we come up with this entire procedure, and number two is to more or less familiarize yourself with a procedure to the point where you can apply it intelligently, to a variety of situations in practice. So these two issues, though, I'm gonna go over the first one. The theoretical explanation is not so complex. The procedure that we're gonna learn is relatively complex. Now, what I noticed in the past was that kids still have a little bit of, difficulty at the end of this class, and I noticed that even when I taught Calc 2, because and the issue is that the problems that are in this book can be readily classified, at least in this section in 4.5, can be readily classified in several small categories. Well, let's say 1, 2, 3. Substitutions with power, substitutions with trig functions, and pretty much that's about it. And you don't get to see a lot of, complex examples. I mean, there are some complex examples, but are artificial. However, in calculus 2, you end up seeing a lot of complex examples that naturally appear there because of the way substitutions work there when you do inverse trig functions or some other types of functions. So I would say, a reasonable thing to do is to review this thing when you take calculus 2, review this thing, folks, and try to take another look at this procedure and take a step back and look at the big picture so you can actually apply this to a new situation that you will see in calculus 2. So again, we are going to be relatively limited in our scope here because we don't really use a lot of sophisticated trigonometry or a lot of sophisticated substitutions. So we're going to learn just the basic ones. But here's the theory. So the theory behind the substitution rule. Well, it's very simple. It's called the chain rule. So here's what the chain rule says. If I take a function, let's say a function f, and if I calculate, So let's denote this by a different letter. So let's say capital F is a function. And I'm gonna do the following thing. I'm gonna do, f of, so f could be something like, let's give an example here. F could be something like, let's say, x squared plus 1. And then I'm going to, or something like x squared. Let's make it even simpler. X squared is a good function. And then I am going to take another function like lowercase g. So lowercase, pay attention here because this is a bit, this is the trick here. So let's say we do x cubed plus 4x, let's say. Now that's g. If we do the composition f circle g, of course we'll get the function. So that's substituting g in the formula of f. So we'll get the function x cubed plus 4x squared. But you know what? It's not really nice to write it like this. So instead of saying g of x, I'm going to say g of some other letter, t. So I'm going to say t cubed plus 4t. And you can see why that would be needed because it's kind of confusing. You know, there's x here, there's x here. So it's kind of messy with x's all the way. So I'm gonna delete this part here and I'm gonna say g of t. And then the composition will be a function of t in this case. So it will be a function of t, which is t cubed plus 4t squared. And that's kind of, that is justice to the big formula. Now, when you do the derivative of that, what you're going to get here is f prime of g, right? The derivative. So if we do d over dt, we get f prime of g of t times g prime of t, which is, now f prime is 2x. So this is going to be 2 times t cubed plus 4t times, and then we're going to have times g prime of t, which is 3t squared plus 4. So this is the derivative of my function f of g. Now in practice, so now you know that this is a derivative, right? So let me write that on a new page. So we said that our function f of x was x squared, g of t was t cubed plus 4t, and we found that d over dt of f of g, let's write it this way, or equivalently f of g of t primed, if you want, is equal, and we just calculated 2 times the quantity t cubed plus 4t times 3t squared plus 4. All right, so this is the derivative. And the derivative being that we are going to look at the opposite way. We're going to look at the antiderivative. So the antiderivative of 2 times t cubed plus 4t times 3t squared plus 4. The antiderivative of this is going to be, you know, the function we started with, which is t cubed plus 4t squared. So this is a function we started with. That's f of g of t, by the way. I forgot to say that f of g of t, it's visible that it's that t cubed plus 4t squared. So this is the antiderivative. So we're going the opposite way. So now if we write antiderivatives, we're going to see something interesting. So we're going to say, and we write antiderivatives with a notation for antiderivatives of 2 times t cubed plus 4t times 3t squared plus 4 dt, right? That's the antiderivative, is t cubed plus 4t squared. So here's what we have, folks. let's look at this situation here. This is, by the way, this is the substitution problem. So why is it called a substitution problem? Here's why. Because if I make a substitution now, so now let's assume we didn't know anything about these things here. We just somehow want to go from this step to this step without knowing any of the given of the above given facts. How do you figure out that the antiderivative of this on the left-hand side is equal to the right-hand side? Well, one way you would say is to write out this product, evaluate the powers, and eventually you'll calculate and you'll find that, which is correct. But we won't do it that way. We're going to try to sort of, knowing what we have above here, sort of figure out the formula for the substitution rule. So first of all, we notice that it played a very important role here in our calculation, this function g, tq plus 4t. So when you do this substitution, that should be visible somewhere in the formula, for instance here. And I am going to, so now there's in practice, you're not going to be given G. You're going to have to figure it out yourself. So I'm going to try to guess that this function plays an important role, and I'm going to use a name for it. I'm going to call it U. U of t equals t cubed plus 4t. One of the things that I notice here and makes this formula really work well is that the remaining part of the formula, 3t squared plus 4, if you look carefully here, that's the derivative of u. So people write that when it comes to integral, they will write du equals, and they will say because u is t cubed plus 4t, they will say, well, that's 3t squared plus 4, and then they will say dt. So I just want to emphasize that these u and t are some labels, but this is where it plays a very important role in keeping track of the variables here. So we're saying that we make a substitution in the initial integral, and by substitution means we intelligently replace all the t formulas by u formulas, where this t cubed plus 4t would get replaced by u, and 3t squared plus 4 dt, the whole thing here at the bottom, at the end, this thing that I circled with my pen is replaced by du. And if that's the case, this formula will look like this: the antiderivative of 2u du. All right, so why 2u? Because u is t cubed plus 4t, so I replace that by u. 2 is still there because it was here. And then 3t squared plus 4, we just noticed that that's the derivative of u, and we write it with dt together, that forms du. But now if we look carefully here, we notice that this thing is really itself is really an antiderivative, because these two symbols, we know that mean the antiderivative of 2u. So that tells me that I have to say, the antiderivative of 2u will be u squared. That's the antiderivative. So that gets rid of these two symbols. And I'll say here u squared, but u squared is not the function I started with. Rather, I would need to write the formula, and that is t cubed plus 4t squared. So we retrieve the formula that's over here by using this substitution, this kind of procedure. That, as I told you, the theory is it comes from the chain rule. So the substitution rule, folks, is more or less, and this is the big end of the theoretical part, is more or less the substitution is the antiderivative of a chain rule, if you want. That is the substitution. but in itself, it has developed as an independent method. So what people do, they will use uh, this substitution thing to to calculate, to figure out antiderivatives of relatively complex expressions. As I said, this is going to be a tool that you should be able to handle. It's mandatory, in fact, in calculus 2. There's no way you can succeed in calculus 2, folks, without understanding substitutions. Now, this may still be vague in your mind, because I just introduced the concept. As I said, I showed you the theory behind it. One can make this very rigorous by using this procedure, but I'm not going to worry about that in particular. So what I'll do, I'll go and I will worry about some examples, and everything else that we'll do here will be a bunch of examples, folks. So here we go. Now, I'm always a little taken aback by the fact that in the book they start with a slightly more complex example. So here's an example, number one. We'll go through a bunch of examples and we'll explain how the substitution rule works. And my hope is that at the end of the hour, you'll have at least a vague idea how this works. We'll come back Monday and we will enforce the concept. And that's pretty much, as I said, that's pretty much where the semester will end with this thing. We still have to do some areas and some volumes, but that's not a major issue, and that's not something that you will see in Calc 2. So right now we're going to do problem 1 from section 4.5. All right, so that will be the integral of cosine of 2x dx. And it says here, use a substitute to calculate this antiderivative, use a substitution, and it tells us what the substitution should be. So again, this is the antiderivative, folks, for those of you who may have missed this lesson or forgot what the notation is. This just means when you see these two symbols, the integral and the dx, antiderivative of cosine of 2x. And now you may be tempted to say, well, can I not guess? Can I not say it's sine? It is that indeed, and in fact, it's a good idea if you can guess it, because the antiderivative, if you find one, you find essentially all. You just add a constant to find the other ones, and there's no penalty if you find it by guessing in calculus 2 at least, as long as you can prove that that's a correct antiderivative. But what I'm going to say here, folks, and in the book they want us to use a U substitution. So use, you know what, I don't like this thing here, so let me delete this. So I'm just going to say use U substitution. It's the method, by the way, the substitution rule is also called the U substitution in some other books. I don't know why U. I can tell you, but substitution. All right, the U substitution. Okay, so it's going to be something like this. So they tell us in the book, you know what? Make the 2x, make it U. If that's the case, then remember that in the formula, when we do the antiderivative, so whenever we make a substitution, we have to figure out what the du would be, the derivative of that, because we will need a du in the formula. So du will be 2dx. Now, let's see what the formula gives us, and let's see what we have to force in there. So this thing here is the antiderivative of, and you can see that you have a 2x, the antiderivative there. So this is the antiderivative of cosine u. 2x would be u. And then dx, which is 1/2 du. Why is that? So again, we need to replace the pieces exactly as they are here in the formula. So cosine is cosine. D2x becomes u because you said that we made a substitution. Then we have to get rid of, we have to replace dx by the exact piece. Now dx itself does not appear in the formula, but you can see it here that if you divide out by 2, you will see that dx is 1/2 du. This is the guy that I want to take and I want to put in here instead of dx. And now this, if you look at the formula carefully, this is the antiderivative of 1/2 cosine u du. So I'm just moving things around here, nothing intelligent. And this antiderivative I know to be 1/2 sine u. So that is the antiderivative. And this is not done, folks. So remember, you start with x, you gotta end up with x. So we're gonna go back and we're gonna track our substitution. It's here 2x. So this is gonna be 1/2 sine of 2x. All right, I'm not even gonna say, well, I'm gonna say plus here, but don't worry about that. So it's a minor issue at this point in time. So right now, folks, convince yourself that this is indeed an antiderivative. So let's convince ourselves. So when we do 1/2 sine of 2x and we prime it, what do we get? Well, we get 1/2, remember the chain rule. So cosine of 2x times, and then there's going to be 2x prime. Well, this is the 2 that's going to simplify this 1, 2 over here and 1/2, and that's going to give us indeed cosine of 2x. So folks, this is indeed the antiderivative of the function we started with, and that is the way the substitution rule works in this particular situation. Before I move any further, I will do a couple more problems, and it's a good idea to actually watch those problems done and then try to figure out if you can actually do more independently. But before I do that, let me just ask a good question here. So how do we know that the substitution should be that u equal 2x? Why is it not something else? Why is it not cosine of 2x or something else, you know, that might make the problem simple? So, there are several issues with that. So you could try any other substitution for that matter, folks. But at the end of the day, you want to make sure that you can replace everything properly. For example, if I tried something like u equal to cosine of 2x, right? Indeed, I would be able to replace this guy by u. But then when I do the derivative, I'm going to get a mess here. So I'm going to get sine of 2x and then times 2x prime, which is 2. So this guy is going to be dx. I don't have a good way to solve for this guy. I would have to divide by 2 sine of 2x. And the formula that I would get would be something like this: the antiderivative of u over sine of 2x. You know what? And it really doesn't work. So that's not something that I would want to do. So not everything is a workable substitution. That's one thing. Now in the book, they tell us that this should be the substitution. They tell us, try this one. How do you know in practice which one to try? Because, you know, you're not going to have a book with you when you solve a practical problem. So let's say you are in Calc 2. They're not going to tell you what the substitutions should be. So how do you figure them out? Well, this is where I said I spotted some sort of a weakness here in our Calc 1 approach. So they only give us, you know, some pre-cooked types of substitutions, and we can easily classify them in 3 categories if you want. But that's not the point. So the point is that we really are going to see only problems with these three types of substitutions. At the end of the day, people will think, oh, these are the ones. So there could be no more, or maybe there is something more that is kind of more exotic. But that's not really true. So we're gonna do. So again, we're gonna go through a number of standard types of substitutions, and the hope is that at the end of this section, so that will be Monday or Tuesday when we finish this, we will be able to have that we would have worked so many substitutions that we will sort of see the green light at the end of the tunnel with these substitutions, where I look at a problem and I kind of make an educated guess, and I try and I sort of guess the correct substitution. So it's a bit of a guessing game, but again, we're trying to educate you how to guess. So that's kind of a main battle with this lesson on substitutions. All right, folks. So that being said, today's lesson I'm going to close by doing a substitution or two with some already prescribed substitutions from the book. Then the next lesson I'm going to more or less do problems without prescribed substitutions. So the problem will be given and you'll have to figure it out. So those are more challenging. But today, because it's our first lesson and we just familiarize ourselves with the concept, we're going to do a prescribed substitution. So that goes for number 2 of section 4.5. All right, so we have this, the integral of x times 2x squared plus 3 to the 4 dx. All right, so this is an antiderivative that we want to calculate, and we are going to do a substitution, and they tell us in the book, do this. U equals 2x squared plus 3. Now, let's analyze a little bit. This is going to work. Why is this a natural choice? Well, here's why, folks. Number one, you can see that simplifies the expression here, makes it u to the 4. And this is kind of fun, this is a really good idea. I can easily deal with powers of something. But then there's still leftovers. There's still the x and there's still dx. Why does that also work? Well, it works because if you look at u prime, the derivative, well, that's 4x. It's not exactly x, but it's 4 times x. So I can figure out what x would be and dx together. So then that really is the trick here. So you write the du, the derivative, and you will see that truly is, folks, 4x dx. And if you separate just x dx, because there's these two guys, this one here and this one here, if you separate the x dx, x dx is going to be 1/4 du. So that is going to be our substitution. That's going to be the substitution. And the integral over there is the integral of, okay, so x dx is 1/4 du. So I'm going to have, I'm going to group these things. So first of all, let's regroup things there. 2x squared plus 3 to the 4 times x dx. And now we're going to substitute. So u substitution, the one that was described earlier here in this circled part, is going to give us, so piece by piece, again, we have 2x squared plus 3 here. That's going to become u to the 4. And then we have x dx here, which is going to become 1/4 du times 1/4 du. And this is going to be, the antiderivative. Let's move these around here. So 1/4 u to the 4 du, and 1/4 u to the 4 is the antiderivative of that is 1/20 u to the 5th, folks. Yeah. And that is going to end up being 1/20 times. And instead of u, I'm going to say 2x squared plus 3 to the fifth. If you want, you can put a constant c here at the end. So folks, this is the antiderivative. Now, if you're curious, you can do the problem yourself. The problem of taking the derivative of this guy here where my mouse is and moving it all the way up to here and figuring out that that really gives you x times 2x squared plus 3 to the 4th. So that's the thing that I wanted to point out. And finally, the exact same type of problem. Okay, so let's do one more problem, and that's going to be our last one today. So number 3 of section 4.5, it says find the antiderivative of x squared times cube root of x cubed plus 1 dx. All right, so where u equals x cubed plus 1. So, so this thing here is also given the substitution, but we need to write this thing. So let's see what du is and why that would be useful. Du is 3x squared, and we put dx. Don't forget to put this dx, very important. And isolate this part here because that's really what you have, x squared and dx over here. So you have, if you rewrite the integral, is going to be x cubed plus 1 to the 1/2. By the way, why is that? Because, square root of x cubed plus 1 is x cubed plus 1 to the 1/2 times, and then we'll have x squared dx. All right. So this is the time to substitution. So use substitution. And we'll finish up a problem here. U to the 1/2, because u is x cubed plus 1 times x squared dx is going to be, if you solve for it here, x squared dx, folks, quickly here, 1/3 du. So we're going to put that here, 1/3 du. And don't worry about these constants. They can be moved around in the integral. So 1/3 u to the 1/2 du. This is a simple antiderivative, and that becomes 1/3 u. Okay, so let's see, it would be u to the antiderivative will be 3/2, and then over here times 2/3. So this ends up being 2/9 times u to the 3/2, and that's not good enough because it's not in x, but we can put it quickly in x. That's 2/9 times x cubed plus 1 to the 3/2. And this is where I'm going to finish the lesson, folks. I'm not going to go any further. Again, I want you to take a look at these antiderivatives as you go home today. As well, you're probably already home, most of you, as you studied today for calculus. But again, focus on antiderivatives to begin with. And these, you have time until Monday. Monday we'll come back to these and we'll review these and we'll do a lot more antiderivatives Monday. So that's my goal, to do substitutions, a lot of substitutions Monday. All right, folks, that's today's lesson. If you have any questions, so I'm going to stop the recording.